Okay, if you're an engineering student, you know differential equations are, well, everywhere. You also know they can be a serious pain to solve. So today, we're diving into one of the most powerful tools in your entire mathematical arsenal, the Laplace transform. And trust me, it's way more than just another formula. It's a whole new way of thinking that turns messy calculus into clean, simple algebra. Think about it. From the current flowing through a circuit to the vibrations shaking a bridge, our entire modern world is built on systems described by differential equations. So, you have to ask, what's the most elegant, the most efficient way to get a handle on them? Well, we're about to find out. So here's our game plan for today. We're going to start with the core magic of the Laplace transform, how it turns calculus into algebra. Then, we'll unlock two really key tools, the differentiation property and the convolution theorem. And we won't just talk about them. We're going to use each one to solve a real initial value problem, step by step.
All right, first up, let's get this fundamental concept down. The best way to think about the Laplace transform is as a kind of brilliant translator. It takes a problem from the world we actually experience, the time domain, and moves it into a much, much friendlier place called the S domain.
And here's the real magic behind it. In the time domain, you're stuck wrestling with derivatives and integrals, right? It can get messy. But once you apply the Laplace transform, you jump over to the S domain, and that same problem just becomes a simple algebraic equation. You solve for your variable there, and then you just transform back. It is an absolutely incredible shortcut.
Now, to really make this work, we need some special tools. You can almost think of them as cheat codes for specific situations. The very first one we're going to master is the differentiation property. This tells us exactly what happens in the S domain when our function in the time domain gets multiplied by t.
And here it is. So what does this actually mean? It says that if you take the Laplace transform of some function, f of t, that's being multiplied by t, the result is just the negative derivative of that function's transform, f of s. So multiplication by t over in the time world becomes differentiation over in the s world. Pretty cool, right? This is where you can really see the beautiful symmetry of how this all works. We just saw that multiplying by t in the time domain turns into differentiation in the s domain. And, a little foreshadowing here, we're going to see soon that this complex-looking thing called convolution in the time domain, it becomes simple multiplication in the s domain. This incredible duality is what gives the whole system its power. All right, that's enough theory for a minute. Let's actually see this property in action. We're going to solve a classic initial value problem, an IVP, and really prove just how effective this whole method is.
Okay, here's our problem. This equation could totally model something like a spring with a mass on it being pushed by an outside force, that cosine of 4t. Now notice something really important. The frequency of that pushing force, 4, matches the natural frequency of the system. That is a recipe for resonance, and the Laplace method is absolutely perfect for showing us exactly what happens.
We're going to follow a really clear four-step plan. First, we just transform the entire differential equation into the S domain. This is great because it automatically includes our initial conditions. Second, we use basic algebra to solve for x of s, which is the transform of our solution. Third, we figure out the inverse transforms for each piece of x of s. And finally, we put them all together to get our answer, x of t. So after transforming the equation and doing a little algebra to solve for x of s, this is what we get. Now that first term should look pretty familiar. It's just a standard sine transform. But what about that second term? Look at the denominator. It's squared. That is a huge red flag, a telltale sign that we're going to need our new friend, the differentiation property, to figure out its inverse. And here is our final solution, back in the familiar time domain. That second term, the one with the t out front, came from that tricky second part of x of s. And you see that t? That isn't just a number. It is the mathematical signature of resonance. It means the amplitude of the oscillation is going to grow and grow over time, something the Laplace method just revealed to us perfectly. Okay, that was pretty impressive. But what happens when our expression in the S domain looks like a product of two familiar transforms? You know, when simple partial fractions just won't cut it. For a situation like that, we need an even more powerful tool, the convolution theorem. So let's ask the question directly. We've gone through the steps, we've solved for our transform solution, and it looks like one known transform, f of s, multiplied by another one, g of s. How in the world do we find the inverse transform of that product? It's not as simple as just multiplying the individual inverse transforms, I can tell you that.
The answer lies in this operation called convolution.
Now, I know that integral looks a little intimidating, but the concept is actually pretty simple. It's just a special way of combining two functions, f of t and g of t, to create a third one. And what's so critical is that this operation, this whole integral, is the direct equivalent of simple multiplication back in the S-domain.
And this is the theorem that brings it all home. It tells us that the inverse Laplace transform of a product, f of s times g of s, is simply equal to the convolution of their individual inverse transforms, f of t and g of t. So what was multiplication in the S-domain becomes convolution in the time domain.
All right, let's get ready for the grand finale. We're going to tackle another initial value problem, but this time we're going to specifically pick one where the convolution theorem is the cleanest, most direct path to the solution.
Here's our second problem. It's a simple-looking first-order system with a forcing function of just t. Now sure, we could probably solve this with other methods you've learned, but we're going to use it to really show off the power and, honestly, the elegance of using the convolution integral.
The plan is pretty similar to before, but with one crucial new step. After we transform and isolate y of s, we are going to intentionally write it as a product of two simpler functions. Then, we'll find the inverse transform of each of those pieces, set up our convolution integral, and just solve it to get our final answer.
Okay, so transforming the equation gives us y of s as the product of 1 over s squared and 1 over s plus 1. Now, from our trusty transform tables, we know the inverse of that first term is t, and the inverse of the second is e to the minus t. That means our solution, y of t, has to be the convolution of those two functions, and that sets up this exact integral right here.
So after you evaluate that integral, which is really just a straightforward integration by parts, we arrive at our final, beautiful, clean solution. This really shows how what looks like a complicated operation, convolution, actually gives us a systematic, almost mechanical way to solve these kinds of problems.
So let's just boil down the essentials from all this. The big idea, the one to always remember, is that Laplace transforms turn hard calculus into easy algebra. We learned two key operational tools, the differentiation property for handling terms like t times sine of t, and the convolution theorem, which is our master tool for dealing with products in the S-domain. Both of these are absolutely essential for solving the IVPs that you are going to see every single day in your classes and your career.
Look, we've just added some incredibly powerful tools to your problem-solving toolkit. These are not just abstract math tricks, they are the exact methods used to analyze and design the electrical, mechanical, and control systems that make our world work. So the only question left to ask is, what are you going to build with them?